Swayam Prabha. Digital India. Educated India.
So, if you look at the shear flow in MD simulations, simple planar shear flow, we discussed a method known as Lees-Edwards method, which is basically a boundary driven flow. In this method, if this is my central simulation box, we think of all these images, periodic images on the top layer and bottom layer to move with a velocity proportional to the shear rate. For example, all the top layer here are moving with a particular velocity to the right, and then all the bottom layer move to the left in the opposite direction with the same velocity. And whenever a particle in the central simulation box were to cross the boundaries on the top or at the bottom, we basically take care of the shear effects when the particle enters the other side. On the other hand, when the particle actually escapes on the left or the right on the same layer, we just do the same kind of periodic boundary condition that we used to do for equilibrium MD simulations. Whereas when a particle moves from to the top boundary box, we saw that how to derive the new position for a particle that escapes at the top. So, apart from simply subtracting the box size, box edge length L, so that would mean if this particle goes here and then we subtract the y component of the position by a value of L, then this particle would have actually come right here in a equilibrium condition. But now we are doing a non-equilibrium simulation where there is a relative flow. So, there is an additional component that has to be subtracted along the x-axis. So, this particle's exposition is subtracted by an amount proportional to the shear rate times box length times delta t. So, this basically means that the particles over a period of time delta t has moved to the left because of an imposed shear. So, we would be adjusting the particle positions not only in the y direction but also in the x direction. So, we saw the last class, we saw how to derive the new positions depending upon whether the particle escapes at the top or at the bottom layer. So, if more particles were to cross the boundary on the top and the bottom, we keep exchanging the particle positions in addition to this periodic boundary condition as well as the shear effects. We will see that eventually a steady state velocity profile will develop within the central simulation box. That means all the particles at the top would have a positive velocities on the x direction, whereas all the particles on the bottom of the box would be moving to the left, and this kind of a linear profile will be imposed if you sufficiently wait long enough. So, this method is known as boundary driven flow using Lees-Edwards boundary conditions. And then once you have this linear profile, we can find what is the stress, and then we can divide the stress by the shear rate, and then you get viscosity. So, even though conceptually this method looks attractive, but then there are some fundamental problems with this method, in the sense this particular boundary driven flow do not have any correspondence to linear response theory. What that basically means is that we cannot relate the fluctuation to the transport quantities. In other words, the Green-Gibbo kind of a relationship cannot be established for this kind of a system. So, the link to the statistical mechanics is broken because of the way that this shear is in an ad hoc basis. So, we do not have a sound theoretical basis to analyze the results. And then if you also look at the time it takes for the steady state velocity profile, it takes so long to get the velocity profile to develop. So, you have to do a lot of simulation for a long time, and until then you have to do the simulation for long enough to get this linear velocity profile. So, these are the two limitations with Lees-Edwards boundary driven flow. So, as an alternative to this particular method and to do it more rigorously with the link to statistical mechanics, modifications are done in the equation of motion itself so as to impose the shear. So, we are going to look at one particular algorithm where the equation of motion itself is perturbed by adding few terms so as to mimic the effect of the shear, and such a modification will have a relationship to statistical mechanics as well as linear response theory, and we have to take care of the periodic boundary conditions there as well. And we will look at one particular method. This is known as SLLOD algorithm. This particular method is also available in GROMACS and LAMPS. And the way this method works is, if you look at on the equations, the first term here that you see is our standard Hamiltonian mechanics. So, we write Hamiltonian as a sum of potential energy and kinetic energy, and then we use Hamiltonian mechanics to derive these equations. In addition to that, now when I have a shear, steady shear imposed on the system, we change the particle velocities and particle momentum, the rate at which it changes, by an additional factors. So, in the particle velocity, we add an effective velocity that comes because of the imposed shear. So, what this means is, if I have a simulation box, we know that the velocity profile should have this kind of profile. So, any particle in the system, depending upon its y coordinate, would have different amount of velocities because of the imposed shear. So, the way we do this SLLOD algorithm is, we start with our standard Hamiltonian mechanics and add additional terms so as to mimic the effect of imposed shear. The effect of imposed shear in the simulation box is that, depending upon the y location of each particle, there is going to be certain velocity in the positive x direction and the negative x direction. So, we are going to look at that and then add the correction to this term is basically r dot del u, where this del u is basically the second order tensor that's basically gradient operator operated on the velocity and then taken a dot product with particle positions. So, this particle position Ri is basically the ith particle's position in the laboratory frame, and when you do r dot del I, this basically gives an effective velocity because of the background shear imposed on the system. Similarly, if you look at the momentum, so here Pi is a peculiar momentum of the ith particle. So, what is mean by peculiar is that it is coming only because of thermal effects, not because of the imposed shear. So, to effect of the imposed shear, we have an additional acceleration term that is given as P dot del u, and this del u is basically will take care of the how much extra force is acting on the particle right here that will change its acceleration. What this basically means is that if a particle escapes from one layer to another layer, it is going to change its velocity. That means there is going to be some acceleration. This term basically mimics what is that acceleration that is added up to the system. So, in the SLLOD algorithm, what we are trying to do is, we take the standard Hamiltonian mechanics applied for equilibrium system and then add an effective velocity and effective acceleration or the effective force via the imposed shear. So, this particular approach apparently it yields the correct nonlinear response to the shear flow, and it can also be shown that this equation of the equation of motions conserves momentum and it produces the required velocity gradient, and along with this we have a boundary condition, so that whenever we have to take care of the re-entry properly. So, now let us look at in detail by having a particular shear field and then how these equations actually get modified. So, this is our standard equation of motion with a flow. Now, suppose I have a very simple planar shear where the flow in the x direction and the gradient in the y direction. So, for this case, this del u can be as a tensor here, this can be defined here, and it can see that there is only one non-zero term and all the other terms are 0. This gamma here is a shear rate defined as dou v rx by dou v ry. This basically means along the direction of the y direction, how the particle's x velocity changes, that is given by the shear rate. So, now we can actually calculate what is this term r dot del u and what is p dot del u for a given shear field. The way in which we shear the system will be encoded in the del u term. So, in the planar shear, which is very simple shear flow, only the one term is actually non-zero. So, now we are going to write this to find the r dot del u, we write everything in a component forms. For example, this r is a vector. So, I, j, k are the unit vectors in x, y, z direction. Rx, Ry, Rz are the x component, y component, z component of the particle position R. We are talking about for a particular particle I. Similarly, this del u is a tensor. You can see that I have written in terms of component form II, Ij, Ik, Ji, Jj, Jk and so on. So you can see that only non-zero term is this and all the other terms are 0 because of the way we have defined our shear. So when you do this dot product of R dot del u, you will see that the product of only this and this term will be non-zero. So you will get R dot del u as R over times gamma times I cap. So this basically means the R dot del u is an effective velocity only happens in the x direction, and how much that is given by the position y position of the particle times the gamma. So when I substitute for R dot del v using this expression for a simple planar shear, we see that the particle's I velocity is basically changed by an amount only along the x direction. Okay. So that means when a particle actually is in a given shear field, it's only the x component velocity is affected and the y component, z component velocities are not affected. Okay. So because of that, we see this only this I cap here. Only the x component velocity is affected by an amount equivalent to the particle's y coordinate times the shear rate. Similarly, we can also calculate what is the effective acceleration or effective force, which is P dot del u. So we again write in component forms Pxi, Pyj, Pzk and then the del u term, and again only the non-zero terms would be the product of these two, and then you can show that the effective acceleration is nothing but Py gamma times the I cap. So when I go and then substitute it here, you get the effective acceleration is again only on the x direction because of the imposed shear, and the amount of acceleration is given by the P, the momentum in the y direction times the gamma that is going to be affected. So you will apply the standard discretization method like leapfrog, velocity Verlet or velocity or Verlet algorithm with these additional compounds. So when you solve these equations with any finite difference method with these additional terms, you will see that the particle reaches particles get a steady state velocity profile across the box. So now we have for the particles in the system, we have how to write the equation of motion so that a planar shear flow can be imposed using these two equations we derived before. Now we have to worry about how to handle particle escaping through the boundary at the top, at the bottom. If the particles leaves in the positive, if the particle leaves on sideways along the same layer, if the particle escapes along the same layer, we can impose the same kind of boundary condition we used to apply for equilibrium conditions. The problem comes only when the particle escapes at the top or at the bottom, for which case we have to deal this. So now what we are going to do is we look at this equation of motion for velocity is changing and how the acceleration is changing. Now if you look at the top surface of the simulation box or the boundary, the top boundary as well as the bottom boundary, we basically write the these box simulation box through certain unit vectors. It can be a cubical shape, then we have three orthogonal vectors for the x, y, z, three orthogonal vectors to describe the box. For example, if you have a cubic box, we have L1 vector as Lxi, and then L2 vector would be so this is basically set of orthogonal vectors that dictates how the particles so this is L1, L1, L2 and L3. So once you have these three unit vectors, you can describe the box. What we want to do is we want to look at how bounded the box boundary itself changes with the time in response to the imposed shear. To see that, we take this equation that we derived for particle and apply the same equation for the boundaries also. But only thing we have to note here is if you look at the dynamics, the rate at which the particle dimensions are changing, there is no momentum acting on this because of there's no particle forces acting on the boundary. So it's just moving only because of the imposed shear. So that's why we have only the shear part by which this is moving. So you can also see the rate of change of the box dimension is only on the x direction, other directions don't change. So if I write this in component form, this k here is basically the k is equal to 1 2 3 4 1 2 3. These are the different unit vectors of the simulation box. So keeping k as an index for each of these unit vectors, if I look at the x component, y component, z component of these boxes, you can see that the y component and z component rate changes are 0. That means your LKY and LKZ, these are basically constant at whatever that was there at the time t equal to 0. So the shear is not really changing the y component and z component of the box dimension. Whereas if you look at the x dimension, it is going to change to this LKY times gamma. So this is shown pictorially here. Let's say this is your simulation box in 2D described by L1 and L2. So L1, L2 can be like this in 2 dimensions, and then this particular law says how the box dimension is changing with respect to time. So you can see that the L1 in this case remains constant because it has only the x component and it remains same, and then if you look at L2, the L2 is actually changing. So initially it was here, and this dynamics will tell you that as another time t, this L2 would have become slanted. Initially it was orthogonal along the y axis, but now with the time the x component of the L2 is changing, so it is going to be like this. So apart from solving the particle positions using Hamiltonian mechanics, we also simultaneously solve how the box length is changing with respect to time. So if you continue this length of the box as a function of time, you see that as t goes to infinity, that means very long time, the theta, which is defined here as the angle between L1 and L2, will keep diminishing, and then in the limit t going to infinity, theta will tend to 0 and L2 will go to infinity. So this will basically make the box go from this to something like this, very skewed. Okay, so to avoid this problem, what we generally do is we start here and then integrate. After some time you see the box length has become like this, and then you do this until you reach a critical angle. Typically this critical angle is taken to be 45 degrees. Once you reach this, you basically map the box dimension to the opposite side. So this goes from this to 135 now. Once you reach this critical angle, you remap the L2, that is the unit vector of the box, to the opposite side by shifting the other side, and then from now onwards you will again continue to do this. You will again integrate. So this box will keep growing, it will go here, and then once you reach 45, you again do this. This is called box flipping. So you keep flipping back and forth so that you don't let this theta tending to 0 and you get a skewed box, and then managing this very skewed box will be a numerically difficult problem. So you let the box deform up to 45 degrees and then you put it back in the other side and again continue to do this. So this box flipping will continue to happen for a very long time, and this also will ensure that the particle crossing the boundary is taken care by this particular boundary method. The other possibility is using a Least-Edwards kind of a boundary condition itself, where we make the particles the simulation boundaries to move at a particular velocity proportional to Ly times gamma times del t in the positive direction, whereas the boundary boxes in the layer below are basically moving in the opposite directions by the same amount. So this is called sliding brick method or the Least-Edwards method. So along with solving the modified SLLOD algorithm, we also change the particle shapes, simulation box shape, so that the periodic boundary condition can be accommodated. So now, so we talked about how to take care of imposing the shear on the particles and how to take care of the boundary, either using a box flip method or the least boundary condition. Now, if you look at the simulation as it goes, you will see that the temperature in the system will keep increasing. This is because that this shear basically induces viscous heating, and the temperature rise will be inevitable. Especially if you simulate the system for a very long time, you will see that the temperature in the system basically increases. So, we also need to do something about setting the temperature to a constant value. So, this problem we also had in equilibrium MD simulations, where if you want to do a constant temperature simulation or a constant pressure simulation, we cannot simply take Newtonian mechanics and solve and expect some constant temperature. So, we have to interfere with the system, couple with a thermal bath, and then exchange heat so that the temperature can be reset. So, now we are going to use a similar approach for a non-equilibrium conditions also. So, in the non-equilibrium conditions, the effecting is coming because of viscous dissipation for the imposed shear, and temperature will keep increasing. So, we are going to apply some thermosetting so that the shear experiment, computer experiment, can be held at constant temperature. So, our strategy here is very similar to how we did thermosetting in equilibrium simulations. That means, we take our equation of motions for planar shear flow. Let us say you can see that these are the additional term that comes because of the imposed shear, and if I solve these equations, I am sure that temperature will keep increasing. So, we want to control the temperature. So, the way you do that is you add a additional term like a friction, which is written as minus alpha times pi. So, pi here is the momentum and alpha is the a coupling parameter. It effectively says there is some sort of a rescaling of the velocities such a way that the velocity will be controlled, by which temperature will be set at a constant value. So, now I am not showing the derivation of this parameter alpha, but the alpha can be calculated, can be actually derived. It basically is proportional to what is the difference between the current temperature and what is the desired temperature, and based on the difference of these two, the parameter alpha will be controlled. So, this is called the Gaussian thermostat, and when you do a non-equilibrium MD simulations with this kind of an approach, having an effective dissipative term here, this is shown that the trajectories will sample a isokinetic ensemble. So, isokinetic ensemble means at every time point we keep the kinetic energy to be constant, and the distribution basically follows the isokinetic ensemble. The other method is a Neuhauser method. So, in Neuhauser method also, if you look at, this is our equation of motion for the planar shear flow, and we do not do anything for the velocity, but for the momentum part, the rate of change of momentum part, we add an effective dissipative term, and this dissipative term again depends on the difference between the imposed temperature and the instantaneous temperature with a constant q, which is basically a user defined control parameter. By choosing properly this value of q, you can control the response with which the temperature is offset here. So, larger q or smaller q will have a very slow or very high response. So, we have to find an optimal q, and it is shown that a Neuhauser thermostat in non-equilibrium conditions like this is basically samples a right canonical ensemble. So, we looked at two methods. One is applying shear using Lees-Edwards boundary flow, the other one is a SLLOD algorithm, and then in either of the cases thermosetting is very important, and the thermosetting can be done either via Neuhauser thermostat or via Gaussian thermostat, which is basically isokinetic ensemble. So, when you think about doing a shear simulation, first we have to see what kind of shear, whether it is a planar shear or not. If it is a planar shear, all this discussion that we have will be applicable. So, now there are other types of non-equilibrium MD simulations. So, you may recall the motivation to do non-equilibrium simulation are twofold. One is we want to calculate the transport coefficients. Other thing is we want to look at the system's response to an imposed external field. These are the two objectives. If we are if our objective is only to find the transport coefficients, we can still get them from equilibrium simulations using Green-Kubo relations, but we noted that such calculations are very noisy, So it's better to do non-Euclidean MD simulation to do that. So in that sense, if you want to look at thermal conductivity or diffusion coefficients, one can set up a non-Euclidean MD simulations for an imposed temperature gradient or an imposed concentration gradient, and then looking at the response, and from those response one can calculate thermal conductivity and diffusion coefficients. So for quantum time, we have looked at only the shear flow, planar shear flow in detail, but a similar approach is possible for other non-Euclidean MD simulations, including extensional flow, heat flow, mass flow, etc. So with that, so we like to summarize that we looked at a new algorithm known as SLLOD algorithm for doing MD simulations for planar shear flow. And the important aspect of the SLLOD algorithm is that we change the particles velocities and accelerate shear, and then the condition effect, so that when the particle whenever the particle leaves the simulation box at the bottom or at the top, it has to be put back by the right changes in the particle positions and velocities. So it can be done either by least Edwards boundary condition or through this box flipping method. And then in addition to that, we also have to take care of the thermosetting of the system, and it can be done either via Nusshoover method or by simply scaling the velocities via a Gaussian thermostat.